To get our minds prepared, let's first solve a simple statics problem before we tackle the more complicated kinematics problem dealing with the ballistic flight of a projectile. Here we have a simple statics problem where we have a mass M attached to a rope that's dangling from two other ropes that are pinned, say, on the side of a cliff. This could be a climber that's suspending himself from the side of a cliff. Now, the lengths of the lines doesn't matter in this case. What we're going to do is try to figure out what the tensions are in the two lines. The tension in this line obviously will be the weight of the mass that's dangling from these two ropes. Now, there'll be a force downward due to the gravitational attraction of the climber mass, and this will be a weight we'll call W, which is just equal to the mass times the gravitational acceleration. And that will be also the tension in this particular line, since the line is aligned itself with a force of gravitational force vector directed to the center of the Earth. However, the tensions in these lines will be different because they're both supporting the weight. So, in order to find the tensions in the line, we first need to look at all the force components in the vertical and the horizontal directions. So, let's draw a reference here in the horizontal, and then we need to know the angles of the two lines, and we'll be giving them that the angle that line 1 makes with the horizontal will be 45 degrees, which we'll call theta 1, and the angle that line 2 makes with respect to the horizontal, let's call that theta 2. Now, there will be two components of forces in each case. In one case, we know that the tension of this line will be pulling upward on this point. So we'll have two force vectors. We'll have the horizontal component and the vertical component. Well, the vertical component of force will be the tension in the line, T1, times the sine of theta 1, and the horizontal component pulling to the right will be T1 times the cosine of theta 1. Now, on the other line, again, we'll have two force vectors. This line with tension T2 will be pulling to the left with force T2 times the cosine of theta 2, and vertically upward at T2 times the sine of theta 2. Alright, we're dealing with a statics problem, and what that means, there's no motion. Nothing is moving. So the sum of the forces in both the horizontal and the vertical directions have to sum to 0. So, in the vertical direction, we sum our forces. Let's choose upward as positive. So, we have T1 times the sine of theta 1 plus T2 times the sine of theta 2, and this force, the weight force, is downward in the negative direction, so we have a minus W for the weight, which is mg, we'll just call it W, is equal to 0. Now, in the horizontal, we sum the forces, and they have to also be 0. Well, let's choose to the right as positive force. So, we have T1 times the cosine of theta 1. T2 is directed to the left, so that's a minus T2 times the cosine of theta 2, and that's also equal to 0. Remember, in statics, we have the sum of the forces is equal to 0. We'll have the sum of the forces in the vertical sum to 0, and the sum of the forces in the horizontal equal to 0. And that's what these two equations represent. This is a statics problem. Now, let's solve the first equation for T2. So, we first have sine theta 1 T1 plus T2 sine theta 2 is equal to W. Solving for T2, we get T2 equals W minus, no, let's not do that yet. Let's keep that equation there, and we'll solve for T2 in this equation, in the horizontal equation. So we have T1 times the cosine of theta 1 is equal to T2 times the cosine of theta 2. Okay, just moving T2 cosine theta 2 to the right hand side. So T2 then is equal to T1 cosine theta 1 over cosine theta 2. Now what we'll do is we'll put this on up into T2 in that equation. So we end up with T1 sine theta 1 plus T2, which is T1 cosine theta 1 over cosine theta 2. That's T2 times the sine of theta 2, and that is equal to the weight W. Now we notice that we have sine theta 2 and cosine theta 2, so sine divided by cosine is tangent, and we can factor out a T1. So we have T1 times the sine of theta 1 plus we have the cosine of theta 1, and then times the tangent of theta 2, and that is equal to the weight. So we can now solve for the tension. T1 is just the weight divided by the sine of theta 1 plus the cosine of theta 1 times the tangent of theta 2. So there we have the tension in line 1. To get the tension in line 2, we just put in for T1 in this equation. So we just multiply this by the cosine of theta 1 divided by the cosine of theta 2 to get the tension in line 2. Now let's put in our values where our theta 1 is 45 degrees and our theta 2 is 30 degrees. I'll rewrite these two equations up on the board here, and then we'll go ahead and solve it exactly for T1 and T2 in terms of the weight. I have now written the equations for the tension in the lines T1 and T2 up here that we just derived. Now, for these particular angles, these are very special angles that I picked so that we can write out the sines and cosines and tangents exactly. The cosine of theta 1 is cosine 45 degrees is square root of 2 over 2. The sine of 45 is also square root of 2 over 2. The cosine of 30 degrees is square root of 3 over 2. And the sine of 30 degrees is 1/2. So the tangent then of theta 2 will be the sine of theta 2, which is 1/2, divided by the cosine of theta 2, which is square root of 3 over 2. So we have 1/2 divided by square root of 3 over 2, which is the square root of 3 over 3. Now, for the tension, let's write T1 over W so we don't have to carry the W over on the right-hand side. So this is 1 over sine of theta 1, which is square root of 2 over 2, plus the cosine of theta 1, square root of 2 over 2, times the tangent of theta 2, which is square root of 3 over 3. Factor out a square root of 2 on each side and multiply numerator and denominator by 6. So we have square root of 2, 6 in the numerator, then 6 times 1/2 is 3, and 6 times square root of 3 over 6 is just square root of 3. So there's the exact number for the tension in one related to the weight of the climber. Now, T1 then, or T2, will be T1 times the cosine of theta 1, which is square root of 2 over 2, divided by the cosine of theta 2, which is the square root of 3 over 2, or this is T1 times the square root of 2 over the square root of 3. So if we multiply T1 over W by square root of 2 over 3, we see that the square root of 2's will cancel and it'll just be square root of 3 times this. So we'll write that out here. I'll get rid of this here. So T2 then will be T1 times the square root of 2 over the square root of 3. T1 then is 6W divided by the square root of 2 times 3 plus the square root of 3, and this is the square root of 2, divided by the square root of 3. Our square root of 2's cancel. We multiply numerator and denominator by the square root of 3. Square root of 3 times the square root of 3 is 3. That goes into 6 twice, so we get T2 is equal to 2W times, these go into 6 twice, that's where we get our 2, and then this is square root of 3 over 3 plus the square root of 3. So that's our tension T2. We could also have written T2 differently, is rather than multiply numerator and denominator by square root of 3 as I did here, we could have started off in this fashion. We had 6W square root of 2 times 3 plus square root of 3, and that is multiplied by square root of 2 divided by the square root of 3, T1. This is T1 square root of 2 over square root of 3. We could have just multiplied through, canceled those two and multiplied through, and if we did that, we would have 6W multiplying through by square root of 3, we end up with 3 plus 3 square root of 3. We factor out of 3, we end up with 2W over 1 plus the square root of 3. Another equivalent form. So, our two tensions then, T2 is that, and then T1 will be 6W over the square root of 2 times 3 plus the square root of 3. Now, we could easily check this to make sure that it's correct, is that the vertical components of the tensions have to sum to the weight W. That is, the two vertical forces have to equal the weight W. So, T1 times the sine of theta 1, well, would be 6W over the square root of 2 times 3 plus the square root of 3, and that's multiplied by the sine of theta 1. Well, sine of 45 degrees is square root of 2 over 2, and to that we add the vertical component on T2, which is T2 is 2W over 1 plus the square root of 3, and that's multiplied by the sine of theta 2. Well, the sine of 30 degrees is 1/2, so that's multiplied by 1/2. So this better sum to W, 1W, when we're done. Well, the square root of 2's cancel, the 2 here cancels with that 2, so we end up with 6W over 2. 2 goes into 6 3 times, so we'll cancel that and write this as 3W over 3 plus the square root of 3 plus W over 1 plus the square root of 3. Well, what does this equal? Well, we put over a common denominator. So we'll have 3 plus the square root of 3 times 1 plus the square root of 3 in the denominator. And then we cross multiply. 3 times 1 plus the square root of 3 will be 3 plus 3 square root of 3. And then 3 plus the square root of 3 times 1 plus 3 plus the square root of 3. Well, this gives us 6 plus 4 square root of 3 in the numerator. And in the denominator, if we multiply this out, we get 3 times 1 plus a cross product, which is 1 plus 3 square roots of 3, which is 4 square root of 3, and then square root of 3 times square root of 3 gives us 3. So we have 3 plus 3, which is 6 plus 4 square root of 3, and indeed that's equal to 1. So it checks out. So there we have it. There's a simple problem in statics.